Hello and welcome to this edition of the Step 7 Odyssey series. In this edition we'll be continuing the discussion of drive control with an encoder by creating a function block and continuing the program. Thank you. In the last video I configured some of the different input, output, static and temporary parameters, and I've added a few here inside of this function block FB10, which we called axis drive. Since then I have also created some code that uses a lot of these variables. As I was programming this, sometimes I would need things like these temporary variables, and so I kind of added them as needed. If you go to any of these folders, you can see what they are. There's a couple of double integers, a couple of reals here, and this was due to, in Siemens Step 7, having to convert one data type to another. So I'll show you a little bit of the code itself and what I did. This is partially simulating the movement of the drive or of the motor, and this will be used to feed into the encoder and generate its pulses also. So the beginning of the code here, and I put a few comments. We had to convert the acceleration, which was in integer form, into a real, and you can see here to do that you have to go through two conversions, integer to double integer, and then from double integer to real. And this is just a kind of a byproduct of how Siemens works. And I did that for the deceleration also, and I put a nice little comment up here to explain why I made those networks. Now this could have been done in statement list even quicker, but some of the followers of this series don't understand statement lists, so we may get into a little bit of that later. But this would have easily been converted into statement list and would have taken less space. This rung increases the speed whenever the start command is active. Of course, the start is a Boolean. It's passed in the input parameters, as is the stop. The stop is assumed to be a normally closed contact, so to turn it off you would press a button or initiate that command, and it would actually open this stop, and then we would no longer collect the speed. So what I'm doing here is simulating the speed control also. So the one shot, what the one shot does is, as long as these two are true, we get a pulse from the internal clock, which I also had to add. This is in the hardware configuration, so I'm using a 100 millisecond pulse, and what it does is if the speed is under whatever your set point is, it adds to the apparent speed, which is the internal actual speed. So I take that acceleration and simply add it to simulate the speed running, since we don't have a real motor and a real encoder. I then do the same for deceleration. So if the stop signal is not on, of course the drive stops and it would decelerate. So this is how you stop the motor. When you do that, your speed will drop to 0. And this network says if you're less than 0, go ahead and move 0 into the variable. So the other thing that I did here is I did create a variable table, and that variable table is used to adjust these parameters. So here it is. I'm going to turn on the glasses, and you can see here that our actual speed is 0. And I'm going to bump this up. I'm going to go ahead and turn off the stop. Actually turn on the stop. Depending on which way you look at it, this is a normally closed contact. So we're going to modify it, and you can see here our actual speed ramped up pretty quick, and that's because our acceleration is set at 10 and my deceleration is set at 2. So watch how slowly this ramps down when I turn this bit off. So put a 0 here, shoot an off into it, and you can see it slows down slowly. So I can adjust my acceleration and deceleration and make this drive ramp up or down proportionally. Now I'm taking the actual speed here as a percentage, so I'm getting 0 to 80, but what I'm going to do in the next step is I'm going to scale this value into actual hertz. So actually I think I'm going to scale it up in RPM rather than hertz. So cycles per minute rather than cycles per second. So I'm going to be multiplying the 0 to 100% range by 175 or so, and that should give me 0 to 1750. Actually, that would be 17.5. So we're going to do that next, and then test this again. So current speed is here. I'm going to go into the code and do a little editing. Once again, this is a function block rather than a function. So rather than moving this directly in here, we can simply multiply instead of moving. So this is another method of changing a box, right? So multiply by real. We will take internal actual speed, multiply by 17.5, and let's see, I'm doing my mental math here. 17 times 100 is 1700. So this would give me at 100%, it would give me 1750, which is basically what I want. And we'll do our actual speed here. Let's see how that works. Delete this. Delete this also, it's empty code. So I've just replaced the move with this, and we'll take a look at how it works. Go ahead and save it, download it, and we'll test it. Put a 1 in here, shoot it in there, and watch it ramped up very quickly to 1400, and we'll give it a little more decel, ramp down a little quicker. Put a 0 in here. So you see how I'm using these variable tables to get these values in here, and you watch it ramp down a little more slowly. So that is basically the part of creating the ramps. So the next thing that we need to do is also accumulate encoder counts. So I'm going to do that. I'm going to go kind of offline here and set that code up, and then come back and we'll discuss it. Okay, back from doing some editing and made a few changes here. First thing I did is created some push buttons, run and stop push buttons, so that we can start and stop the motor from the simulator. So you see here we have some start and stop push buttons, we have some forward and reverse push buttons, and I've also added a set home push button here. So now everything is going to be run from the variable table and the simulator itself. Now this simulator, of course, could have been a regular PLC, but you still would have needed either a variable table or an HMI programmed to do that. The other thing that I did was I removed the function block call from here in this sequence, and I put it in the simulation sequence where it belonged. So this is the simulation sequence, and this is the drive simulation, the thing that generates the speed and now generates also the encoder position. So I added these signals that we created in the data blocks and had them drive these encoder positions and speeds. We'll take a quick look at the actual code and see what I did here. Okay, there's our increase speed, decrease speed, ensure speed can't drop below 0. This is all the stuff that was originally in there. And then pass the speed out as an actual speed. So this code, what this does is if you're in forward mode, I'm using a 200 millisecond pulse and a one shot, and I'm actually just adding the internal speed every 200 milliseconds to an encoder count. Now in real life, of course, your encoder would be based on how many pulses the encoder was, and every time the motor revolved one time, you would get that many pulses, and you would accumulate pulses into a high-speed counter card. That high-speed counter card operates independently of the program. So if I want a signal to come on from the card to say stop at say 10,000 pulses, it's going to do that regardless of the position in the scan of the PLC. So it's independent of the scan. That's why high-speed counter cards cost a little more. So if I'm going forward, I do that. I add the number. We were in real numbers because the actual speed, of course, is real. So I went ahead and made a real version of the encoder. If we are in reverse, then we accumulate encoder counts in reverse, which is really subtracting the encoder counts. That's what's going on here. And subtract the integer speed from the encoder counts. And then if I press the set home push button, I simply move 0 into the counts. And then in this case, I had to once again convert from a real number into a double integer because we made our encoder counts as a dent. And this is typical. You would usually have encoder counts as a double integer. You could count up to about 2 billion counts that way. Of course, you wouldn't use real for that. So I generate those counts as real numbers, but then I pass them out as a double integer. And of course, that makes the code, right, the block look like this. We haven't done anything with the alarm yet, and we won't during these couple of videos. But there's my start, stop, forward, reverse, my commanded speed %, my acceleration and deceleration, my actual speed in hertz passed out, and my encoder position. Let's go ahead and test it, show you how that works. So right now I'm commanding the speed to be at 80, but of course I'm stopped. I'm now using these push buttons to run the drive. This is going to run in auto or manual. It's kind of independent, but we will modify it later. This would typically, if I'm starting and stopping things with a push button, I would be in manual mode like this, right? Manual mode. So in auto mode, we're going to do something a little bit different here so that we can test where this encoder stops when I give it a stop command. In any case, I'm going to press the run button, and we're going to put it in forward first. And press the run button, and you see here we ramped up to speed, and we're constantly accumulating those encoder pulses. Of course, that's not a real encoder, it's just the counts we generated. When I hit stop, I ramp down and I stop accumulating encoder pulses. If I go in reverse, then I say run, and of course I'm counting down at this point. So that's the way that works. So we will stop the drive, we ramp down, and we are at currently 1480 pulses. And then if I want to, I can reset this to 0. So I set home. Typically what goes on here with homing is you would move back to a sensor of some kind, an external sensor on the actuator, and when you hit that sensor you would say stop, and then once the actuator was detected to be in the 0 position, then you would set it home, and you wouldn't be doing that with a push button, you'd do it with a command in your auto sequence. So this is going to complete this video. We're going to finish this up here, and this takes care of everything as far as simulation. So we've been able to move the drive forward, move the drive in reverse, and stop it. And the next thing we'll talk about in the next video is how to do that in auto mode and some methods of creeping to a stop position if you were using a VFD. Of course, a servo, I could simply tell it that I want it to go to a position of, I don't know, 3 meters or something like that on an actuator, and the encoder count would be scaled, and it would stop probably within a couple of millimeters or even micrometers of the correct position. But you can't do that with a VFD, which is why I was asked this question in our little Facebook automation group, which is what inspired this series. In any case, that is the end of the video. Thank you.